to this day 27 learning non-linear and nonlinear SVMs. So this is a new chapter altogether learning about SVMs. So it would be an interesting. Hope this session would be fun and a new learning for many of you. We have looked at we have looked at linear logistic regression, where which helps us classify certain problems. In this SVM stands for support vector machines, is a supervised learning algorithm that can be used for classification and regression. For example, let's say we for classification, let's say we have many examples, like whether we want to classify an email as spam or not spam, or image also is image classification is also a technique, and there can be many others, right? So in SVM, we create a decision boundary that separates two different classes, and the distance between the two classes, like a class A, class 2, for example, this can be a class A, and this can be uh, class 1 and class 0. Class 0, uh, class 1 to the boundary line, and class 0 to boundary line. This margin should be clearly separable. So this is where SVM comes in handy. So there are few things to know. Decision boundary, which is the line that we see here that separates two classes, that's decision boundary. Margin is distance between the closest examples. Closest examples as in this is an data point from class 1, and this is a data point from class 0. So this is one thing. And next thing is support vectors. These are the data points that we training examples closest to the boundary. So there are terms like hard margin and soft margin, which we will go through, and also C parameter or hyperparameter. So we are loading a simple iris dataset. That's something with respect to iris sentosa, virginica, or versicolor. Those are the classification. But here we are specifically look at versicolor and virginica. So if you remember, virginica and versicolor had few data points very close to each other. So this is where SVM also takes that minute correction and brings out the best result. Linear SVM classifier is a decision function where W is weight vector, and it is X with respect to input features, B and bias and intercept. So why we maximize the margin? So if there is largest possible gap between two classes, we can easily separate, or we can quickly say this is of a versicolor or this is of a virginica or something like that. So that's where margin parameter comes in handy, right? So linear classifier has this kind of a function, and we have a linear classifier method also, and we are importing here standard scalar from sklearn SVM module, right? So yeah, those are few things. So next is we have this piece of code which gives us training accuracy, and also we could visualize the linear SVM decision boundary, something like this. And we have C parameters, everything put out here, right? So that's one thing to note. Next is hard versus soft margin. So we came across this parameter at the start. So hard margin and soft margin, it's so one thing is you could see the decision boundary here. So there might be certain times where you would need to place it absolutely perfect, separating the distance equally. So that's hard margin, where all the training separates all the training examples correctly. This is also a reason of overfitting, and keeps all the examples outside the margin. This maximizes the margin distance between the 2 points also. In case of soft margin, it is a rough kind of a uh, decision boundary, which also might include noise, outliers, and overlapping classes, and sometimes mislabeled examples. But all in all, this could classify a bunch of data points, about 90%, as you could see here. This can also be a part of soft margin. So that's about the difference between hard and soft margin. Understanding the C parameter or hyperparameter helps in deciding how we want our hard margin or soft margin. So the larger C parameter would mean weaker regularization, which means it's of a category of hard margin, while the other one is soft margin. So that's a quick thing. So you could play around with C parameter and see how the line shifts, right? So I've got few examples here. Next is nonlinear SVM. This is where we deal with polynomial features where there are degree coefficients to the feature variables. So here we are taking an example of Moon's type dataset. There might be other datasets also, but Moon's dataset and such data points is usually solved with nonlinear SVM. So in nonlinear SVM, we first have a degree parameter which helps. This is a linear SVM or non-linear dataset. So this is Moon's dataset, and you could see more data points not being classified properly. In case of non-linear SVM, we have polynomial features which have a degree coefficient to it in its function. So that's one thing to know. So for such a model, we can have degree value set as 2, 3 or something like this. This would polynomial features with degree 2 and 3, and this would result in classifier something like this, right? So that would be the way to go about. And next is polynomial kernel. So this is a SV. So this would be a single line of a function which could take in all three parameters like degree, C parameter, and coefficient function, and this would easily create the same kind of combinations with the degree changes as well. So here we are also considering three different things in one single polynomial kernel. So we can specify it as poly. Please do let me know if you find any other polynomial type or any other values that you could send in kernel function, right? So you could also specify degree, coefficient, and C parameter. So this could result in such a classifier as well. So those were few learning items for today. Hope you found this video helpful. Please do check this IPython notebook for reference. Hope you found this video helpful. Please do like and share my video. Thank you.